All right, there still seems to be a number of questions about exercise 8.3, and then exercise 8.4 is one and the same, so series and parallel reactions in an isothermal CSTR. And so I want to try and take a second shot at trying to walk you through how to set this thing up and explain what everything means. Okay, and so before we even look at the specific case of 8.3, I'm going to look at section 8.14, which just talks about a single reaction in a CSTR. And what we have here, and then how we can extend that to exercise 8.3, and then ultimately exercise 8.4. Okay, and so exercise 8.3 is just meant to be an extension of the example problem considered here. Okay, and so if I look at that first subsection, 8.14.1, just goes through the derivation of our mole balance design equation. Okay, and so what I'm going to do is I'm going to go over to a piece of paper as if this were a whiteboard in class, pick up with this equation. You can see how it's derived by reading, and then talk about how we would build upon that for 8.3 and how we would get an error function out of it and the like. Okay, so in the example section, all right, so we're considering a single reaction of A goes to B in an isothermal CSTR. So my mole balance design equation takes the form of, okay, so I'd have a mole balance design equation for each species. Okay, so for species A, okay, I have Na dot minus Na dot naught. Okay, so Na dot, this is the molar flow rate of A leaving my reactor. Na dot naught is the molar flow rate of A entering my reactor. Okay, so this is molar flow rate exiting minus molar flow rate coming in. And that's going to be equal to nu A V times R. Okay, so now let me explain what all this means. Okay, so R is my general rate expression. Okay, nu A is the stoichiometric coefficient of A. Okay, nu A times R is equivalent to my species-specific rate. Okay, so what does this mean? Okay, so looking at my reaction A goes to B, I know for every mole of A that's consumed, a mole of B is produced. Right? So the consumption of A and production of B is constrained by the stoichiometry of my reaction. Right? So R, right? So when we say it's our general rate, right? It's our general rate because if we multiply by the stoichiometric coefficient of the appropriate component in that reaction, it becomes our species-specific rate. Okay, so for example here, right, R would be some, positive number, right? So it's, some rate, some net rate of generation or consumption. So nu A, stoichiometric coefficient of A, would be -1. Okay, so -1 times R would give me my species-specific rate. Okay, multiplying by the stoichiometric coefficient of A, -1, my reactant, it becomes some negative value. All right, so it corresponds to a consumption term. All right, and so if I look at my left-hand side, molar flow rate exiting relative to what comes in, okay, this tells me what's coming out is less than what's coming in, right? Because this side's going to have to be negative. Okay, so nu A times R, significance of multiplying my general rate expression by my stoichiometric coefficient is it makes it my species-specific rate. Significance of V here is R. Okay, so here we're talking about a homogeneous bulk phase reaction. Okay, and so the general idea here is we're trying to make our rate an intensive quantity. Okay, and so we make it intensive by normalizing with respect to the volume of our system. All right, so that if I were to measure kinetic data for this reaction A goes to B in some small laboratory scale reactor, this gives me the ability then to, say, scale it up and use those kinetics to describe a system in some much larger, say, industrial setting, okay, hypothetically. Okay, so where V comes in is it's just V times R makes my rate extensive again, okay, because here I'm dealing with extensive molar flow rates. Okay, cool. All right, so another way to write this would be, say, V, my volume, times RA, where RA is just nu A times R, my species-specific rate. Okay, so that'd be, say, my mole balance design equation for E, and I could equivalently write a mole balance design equation or for A, I could equivalently write a mole balance design equation for B, which would take exactly the same form. Okay. So my mole balance design equation for B would be exactly the same. All I do is replace A with B. Okay. And now, for completeness, so looking at our reaction here, okay, we would have that the stoichiometric coefficient of A is -1. Okay. It's a reactant, so it's negative. And then, its coefficient is just 1. My coefficient of my balance reaction is just 1, so it's -1. Stoichiometric coefficient of B is +1. Okay? So B is a product, it's being produced. A is my reactant, it's being consumed. Okay? Cool. And then the rate expression we're given takes the form of R is equal to K, a rate constant, times, we're told, Ca. All right, concentration of A. So it's proportional to the concentration of A. Okay. Then K, my rate constant, is typically described using an Arrhenius equation. Okay, so K takes the form of K naught. K naught's my pre-exponential term, times the exponential of negative E. E is my activation energy, which is constant, divided by RT. Okay, so we're told we have an isothermal CSTR. Okay, so T is constant, so E is constant, and K naught are constant. Okay, so given the value of K naught, E, and T, and then you can use your molar gas constant. Look it up in Wikipedia or NIST. I can evaluate K. Okay, then once I have K, okay, so then R is equal to K times Ca. Okay, where Ca is essentially going to be unknown. It's an unknown concentration exiting my reaction. Right, but I could plug R, so I could plug in those constants to get to K. Then once I have K, I could plug this expression up here in for R. Okay. All right. So as I talk a little more before we kind of get things set up. Okay. Here we're dealing with molar flow rates. Okay. And so typically I would know, say, molar flow rate entering my reactor, but I'm not going to know what's coming out, and that's what I want to solve for. Right. Molar flow rate and concentration are related. How they're related is, well, let's just look at units. Okay, so my molar flow rate of, say, species I will take units of moles, and I'll just say per second, or essentially it's just moles per time. Concentration of concentration of some species I. Okay, we'll have units of moles per volume. Okay, it's going to be a molar concentration. Okay, so here I have moles per second, moles per volume. Okay, so in order to get from molar flow rate to concentration or vice versa, the quantity that I'm going to need is a molar flow rate, or a volumetric flow rate. Okay, so V dot, my volumetric flow rate, will have units of volume per time, or I'll write volume per second since I wrote volume per seconds there. Okay, so then just comparing my units, I would see that Ni dot, right, would be equivalent to Ci times V dot. Okay. So the one assumption we're told that we can make in the example problem is that, let's assume our volumetric flow rate is constant. Okay. So we have an isothermal reaction, and our reactants and products are also very dilute. Okay. So they're very dilute in my incoming stream and exiting stream. So assuming my volumetric flow rate is constant is going to be a very good approximation in this case, or a very good assumption. So assuming my volumetric flow rate is constant, what that allows me to do is, if I look at, say, the left-hand side of these equations, is I could say Na dot minus Na dot naught would be equivalent to V dot times Ca, concentration of A in my exiting stream, minus Ca naught, concentration in my entering stream. Okay, so that's going to be assumption 1, all right, and that's how we'll use that. So my mole balance design equation will take the form now of V dot times Ca minus Ca naught, okay, and I'm just going to look at A now in the interest of space. And on the right-hand side, we had nu A times V times R, where that's going to be nu A times V times KCA. Okay, and K, is this term, which is just constant. Okay, cool. Okay, and so we could do the same thing for B, but before we do that, okay, the next thing we're going to do is I'm going to divide through by V dot. Okay, so I'm going to rewrite this as CA minus CA naught is equal to nu A times V over V dot times R. Okay, so now if I look at V and V dot, okay, V is going to have units of volume. Okay, V dot is going to have units of volume per time. Okay, so therefore V divided by V dot will have units of time. Okay, all right, so now if I'm trying to design a CSTR, right, essentially you can often encounter two different scenarios, right? So one scenario would be I have some inlet stream of known concentration and known volumetric flow rate, okay? And what I want to do is I'm trying to design, say, a CSTR. Right? I'm going to build a CSTR. And so my design parameter, say I want to look at controlling, is the volume of my reactor so that I can achieve an exit stream of a given product composition, right? The other scenario would be I have an existing CSTR of known volume that I had from, say, a previous process that I want to repurpose for a new problem. And so I can't necessarily easily resize the tank. That's been engineered already. But maybe what I can do is I have a control valve, and I can use that to control the volumetric flow rate exiting my tank, right? Or entering my tank. So another possible scenario might be having an existing tank and then controlling a valve to control the volumetric flow rate entering my tank to achieve a given exit concentration. Right? So they're kind of two different scenarios that you can play with, or even use one together. So how we can kind of generalize these two problems is V over V dot has units of time, okay? And so oftentimes we rename V over V dot with the quantity tau, okay? And so tau could be called a number of things. One way that's commonly thought of or referred to is the mean residence time. Okay, and so the idea is in a CSTR, fluid element enters my reactor, it's perfectly mixed, and then I have some exit stream leaving my reactor, so that the net rate of accumulation in the tank is, say, 0. Right? It's a steady state operation. So the idea with tau, or the idea of tau is the mean time that a fluid element remains in my reactor. Right? So if I picture a bunch of little packets of fluid entering my reactor, it enters, is perfectly mixed. On average, how much time does that packet spend in my reactor before it comes out in the exiting stream, right? And so tau, right? And so tau then gives you the ratio of V over V dot. And so if we just play around with tau, and if I know volume, then that gives me, say, volumetric flow rate, right? If I'm solving for tau, or if I know volumetric flow rate from that first scenario, then I can solve for V. All right, so it just kind of generalizes the problem. Okay, so the equations is we're going to use them in our problem. I'm going to rewrite as CA minus CA naught is equal to tau times nu AR. Okay, where again nu AR, okay, is going to be in this case nu A times K times CA, where K is just my Arrhenius expression. Okay, and we'll write that down in a second. And then for B, I'd have CB minus CB naught is equal to tau times nu B R, or that's tau times nu B K CA. All right, so now if I think about what we have, all right, and kind of thinking about this in the context of our problem, okay, these are what are going to compromise my air functions, okay? And so how I would convert these to air functions is this is equivalent to CA minus CA naught minus tau nu AR is equal to 0. CB minus CB naught minus tau nu BR is equal to 0. Okay? Where we know CA naught, okay, from the problem statement, I believe was 2 molars, okay, 2 moles per liter, Initially, we don't have any B. Okay. Now we said stoichiometric coefficient of A is equal to -1. Stoichiometric coefficient of B is equal to 1. Okay. Then as far as R is concerned, okay, sorry, I'm going to have to run on this next piece of paper, but I'll try here. Okay. R was equal to KCA, where K was equal to K naught times the exponential of -E over RT. Okay, where E is my activation energy is constant. We have an isothermal CSTR, so RT is constant, and K naught is given to us as constant, right? So K is just constant. I can calculate this, okay, but then I'd have this, K, which is known constant, times CA term, up here. Okay, cool. All right, so then if I plug that in, right, essentially the only unknowns in this equation would be CA, CB, and tau. Okay, but if I specify the value of tau, like for this tau, what is the concentration of A and B leaving my reactor? It reduces to a system of two equations with two unknowns. Okay, so I have a system of two equations with two unknowns that I could solve using FSolve. All right, and so if I wanted to say calculate the concentration of A and B as a function of tau, what I might do is create a vector of tau values, then create a for loop where I loop over that vector of tau values. For each value of tau, I can then solve for CA and CB, collect those in two vectors, and then at the end of the for loop I have concentration of A, concentration of B as a function of tau, right? Because I have the values at those corresponding tau values. Okay? Then what changes for the next problem? Okay, so hopefully this makes sense. So it gives you an idea of air functions. My initial concentration of A for problem 3, I'm just going to take from the example problem because it's just building off of it. And then values of your rate constant are given. Oh, and the only note I'll make about this Arrhenius expression is remember this term is going to be dimensionless. So the E that's given the problem statement, I believe, uses kcals per mole. Okay, so either take that and convert to joules per mole, or make sure you use R in kilocalories per mole Kelvin units, so that this is dimensionless. Okay. All right. So then, what changes in say problem 8.3? Okay. So in problem 8.3, okay, let's first consider the case of series reactions. Okay. So what's meant by series reactions? Okay. So in reaction 1, I'm going to have A reacting to form B. Okay, so B is my desired product. Okay, but now as compared to that example problem, we're going to have an undesired. Actually, this is a parallel case. So I said series. So series. Okay, so A is going to react to form B. So here's the reactant that's going into my reactor. Here's my desired product. But I'm going to have a side reaction. Okay, and so let me label this as series. Okay, so when I give you these notes. Okay. So I'm going to have an undesired side reaction in which B, my desired product, reacts to form C. Okay, and so C is going to be our undesired product in this example. Okay, so what changes? Okay, well, if we consider our final mole balance design equation for A. Okay, so for a single reaction, our mole balance design equation, as we just wrote it, was Ca minus Ca naught was equal to tau times nu A times R. I'm just making sure I have all my values accounted for. Okay, so again, I'm just going up here. Okay, Ca minus Ca naught is equal to tau nu A R. Okay, so this is for a single reaction. Okay, so what changes here is now I have multiple reactions. Okay, so remember nu AR, that's my species-specific rate. So, in say reaction R, single reaction that's occurring, it gives me the net rate of generation or consumption of species A. So what happens when I have multiple reactions is I need to consider the ability of each species to be produced and consumed in each of those reactions. And so what I need in my mole balance design equation then is the sum of those net rates of generations and consumptions due to each reaction. Okay. And so what happens is for multiple reactions, okay, I'm going to change this so it's Ca minus Ca naught is equal to tau. Okay, and then in general, it'll be, say, a sum over all reactions J. Okay. Stoichiometric coefficient of each species in each reaction times the general rate expression for each reaction. Okay. So for our problem, we would have, we'll write a mole balance design equation for A, B, and C. Okay, they're all going to look exactly the same. Okay, for A, I'd have Ca minus Ca naught is equal to tau. Okay, then let me put this in brackets since we're writing it for the first time. Okay, stoichiometric coefficient of A in reaction 1 times my general rate expression for reaction 1 plus nu A2 R2. Okay, I can write one for B, Cb minus Cb naught is equal to tau nu B1 R1 plus nu B2 R2. Okay, and then finally C would be Cc minus Cc naught is equal to tau nu C1 R1 plus nu C2 R2. Okay, beautiful. Okay, so again, all right, we're going to know the concentration of A, B, and C entering my reactor. And what we're going to want to try and solve for is the concentration of A, B, and C exiting for a given value of tau. Okay. So, okay, just in the interest of being able to have the reactions up at the same time, okay, let me write down our stoichiometric coefficients over here. Okay. Remember, if you're a reactant, your stoichiometric coefficient is negative. If it's a product, it's positive. Okay. And so, looking at A, stoichiometric coefficient of A in reaction 1, this reaction would be negative 1. Okay, looking at reaction 2, the stoichiometric coefficient of A in reaction 2 is 0. Okay, so I like to write my mole balance design equations out in this general form, and then just use stoichiometric coefficients of 0 if they're not present. Why? Because then I can just take my series code, resave it for the parallel case, and just update my stoichiometric coefficients and rate expressions, right? Because the underlying equations aren't the same. It's just, the stoichiometric coefficients will change. Okay, but more on that in a second, right? So stoichiometric coefficient of B in reaction 1 is positive 1. Stoichiometric coefficient of B in reaction 2 is negative 1. Stoichiometric coefficient of C in reaction 1 is 0. Stoichiometric coefficient of C in reaction 2 is a positive 1. Okay, cool. Okay, so there's my stoichiometric coefficients. Now let's talk about initial concentration, since that was a tad bit confusing too. Okay, so now the concentration of A going in, okay, it's going to be 2 molars. So my original intention when I created this problem was that it would just be a continuation of the example problem. This is something where, if we would have been able to meet in class, we could have communicated this, or I could have communicated a little better. But this is just meant, this first problem, 8.3, is just meant to be a continuation of the example. So we're going to deal with the same system, only now we have these side reactions happening. Okay, so the initial concentration of A will be 2 molars. And then just like before, we'll start with no B or C in our reaction, or in our inlet stream. Okay, cool. Then when it comes to R1, okay, R1 is the same reaction that we had in the example problem. So R1 is going to be K1 Ca. It's going to be first order in A. So I write a subscript 1 now for R and K, because these are my general rate expression and then rate constant for reaction 1. Okay, K1 is going to be computed just like before. So K1 is going to be K01, so my pre-exponential term for reaction 1, just like in the example problem, times exponential exponential, I don't know, I'm going with beta there, exponential of negative e over RT. Okay, now I'm going to write this as E. I'm not going to put a subscript on here because in all these problems we're going to use the same activation energy for both reactions. So I'm just going to write it as E, right? And you're going to be given the activation energy, which will be the same in our second reaction. Know that in our 8.4, our next problem, the activation energy is not the same for both, but here it is. Okay, negative E, which you're given over RT. Now R2, okay, is going to be given by K2, and then it's going to be first order in B, right? So here I have B forming, right? B's reacting to form C, so it's going to be first order my reactant B. Okay, so R2 is going to be K2 times CB, where K2 is going to be equal to K02 times the exponential of negative E over RT. Okay, where this is the same negative E over RT as we are looking at in reaction 1, which is the same as the example problem. Okay, and so you're not necessarily given a value of K02, but what I ask you to look at is just different scenarios where K02 is just a different multiple of K01. All right, so in one case you're going to look at one K01 and K02 are the same. Okay, then you'll look at one K01 is 10 times faster or 10 times larger than K02, and then you're going to look at the third scenario where K01 is 10 times smaller than K02. Right, if I have all the numbers correct in my head. Okay, so you're not given a value of K02, but all I ask you to do is look at 3 different scenarios where you can look at K02 as a multiple of K01. And so essentially, we're just trying to compare then the behavior of our series and parallel case as a function of the relative size of those pre-exponential terms. Okay? Cool. So looking at my mole balance design equations, okay, if I were to make these air functions, right, I just bring the right-hand side over to the left. Okay, and so I'll have a system of 3 equations. Okay, and how I get 3 unknowns is, well, CA, CB, and CC are my unknowns. So that's what I'm trying to solve for. Okay, so these are unknown. Okay, we'll solve for a specific case of tau. Oops. Okay, we know our inlet concentrations. I know my stoichiometric coefficients. In terms of R1 and R2, I know the pre-exponential term. Okay, what I don't know is CA and CB, right? But those are, have already been accounted for in unknown variables. Okay, so basically, it's going to be similar to that example problem. So for a specific value of tau, I have 3 unknowns: CA, CB, and CC. But I have 3 equations that I can simultaneously solve to solve for CA, CB, and CC. So how I would tackle this in the problem is I would say create a vector of taus, then set up a for loop where I loop over those values of tau, and for each value of tau, I can then solve for CA, CB, and CC. I can solve for my unknowns. Okay, cool. And then once I have them, then you can worry about calculating the stats that are given the problem or asked for. So I don't believe they ask you for fractional conversion. We looked at it in the example problem. But, all, say, FA would mean is if A is my, reactant. So that's the reactant that I'm feeding into my reactor to create some desired product. And so it, is often useful to monitor and the relative value in the exiting stream, so I know how much of what went in has been consumed, right? And so it'd be what went in relative to what went out, normalized but by what went in, right? So it's the fraction of what went in that's been consumed. Okay, or equivalently, all right, here now we've seen we can write this as CA naught minus CA over CA naught. The other quantity that we're looking at is selectivity of B over C. Okay, so B is my desired product, C is my undesired product. Okay, so all selectivity is the concentration of B over C. Okay, and note, I think I have a typo in the problem statement. Right, let me bring back to the problem statement, and I'll fix it when I re-upload this with another link to the screencast, where this should be CB over CC. Okay. So there's selectivity, which we're also asked about. Just take care when plotting this. So if I look at, get my mouse active again. So I look at this problem. So initially, when I just have A present, my first reaction, will proceed. But when I essentially, at time equals 0, I'll essentially have very little or virtually no B. This reaction is going to be incredibly small, and so I'm going to have even less C. And so at small times, your selectivity is going to be huge. All right, and so for the series case, just be conscious when you're plotting. If you have a huge number initially, that's what's going on. It's just a numerical issue. Okay, but that's how you would tackle it. Okay, and that's a series case. Okay, and so let me give you a basic idea then of the parallel case. Okay, so let's insert a new page. All right, so if I consider parallel, all right, what changes, right? And so we'll do this one a little more quickly. Okay, so parallel, now I'm going to have A goes to B, and then A is also reacting in this undesired side reaction, right, in which A is reacting to form C, my undesired product. So B is my desired product, B is undesired. Okay, so mole balance design equations are identical as before. Okay, Ca minus Ca naught is equal to tau times nu A1 V times R. Oh, I'm getting mixed up. I'm mixing everything up with before. Tau times nu A1 times R, 1 plus nu A2 R2. Okay. Cb minus Cb naught is equal to tau nu B2 R2. Ugh. Sorry, I'm getting all scrambled now. Nu B1 R1 plus nu B2 R2. Okay, and Cc minus Cc naught is equal to tau nu C1 R1 plus nu C2 R2. Okay, if I want to write these as air functions, then I just bring, say, the right-hand side over to the left-hand side. Okay, now for my parallel case, what changes? My stoichiometric coefficients. Okay, so now nu A1 is equal to -1. Now A is also my reactant in reaction 2, so it's -1 there as well. B, nu B1 is going to be +1. It's a product in reaction 1, and it's not present in reaction 2. For C, nu C1, C is not present in reaction 1, so it's 0. Nu C2 is +1. Right? It's a product of reaction 2. Initial concentrations are going to be the same, so we'll still have Ca naught is 2 molars, Cb naught is 0, and Cc naught is 0, so those will remain the same. My rate expressions, so R1 is going to be identical. Okay, R1, just like before, will be K1 times Ca, first order my reactant, where K1 is going to be equal to K naught 1. Same K naught 1 as the example problem, and whatever you would have just used for series, times exponential of -E over RT. Okay, so this is the same E, that's the same RT, that's the same K naught as the example problem, same as you would use in both series and parallel. Now the other change besides my stoichiometric coefficients, so stoichiometric coefficients would change. The other thing that would change is R2, okay, is first order in our reactant for reaction 2, which is also Ca. Okay, where K2 will be K naught 2 times exponential of -E over RT, same E and RT. Okay, and again, K naught 2 is just going to be a multiple of K naught 1. Okay, so it's virtually the same problem. You would create, say, a vector of tau values, set up a for loop then where you loop over those values of tau. Each loop iteration you solve for Ca, Cb, and Cc for that specific value of tau, collect those in vectors for A, B, and C, And then at the end of the for loop, you have concentration of A, concentration of B, concentration of C at those corresponding tau values, right? And then you can, create the desired graphs and compute the desired quantities with those. Okay, cool. All right. If there's any additional questions on 8.3 and 8.4, by all means let me know. Okay, and just for completeness, all right, if I go back to the example, okay, in 8.3, when we're looking for, my pre-exponential term is this 2.4 times 10 to the 8 seconds inverse. And here's my activation energy, 15.3 kcals per mole. All right, so that's where those values are. Okay, so that's 8.3. Okay, I report those here as well. Okay, and then 8.4 is essentially one and the same too. It's just the reaction's changing. Right, now I have A plus B goes to D, desired product, A plus B goes to U, undesired product, and we have our rate expressions here. Okay, I guess one thing I'd point out, so if I look at, here, so if these are my mole balance design equations, remember I plug in R2 here, right, that's, K2 times CA, right, and so from within your air function, that's where you would, plug in R1. So K is a constant, so I could say pre-calculate that at the onset of my problem and pass it to my air function via an anonymous function. But then, that plug in here, right, I would have, K1, which could be a constant, times CA there. That would be in my air function. Okay. Hopefully that helps. Hopefully then you can generalize that for 8.4. It's, going through the same exercise, just updating. You'd have a mole balance design equation for, looks like, A, B, D, and U. So I'll have 4 equations with 4 unknowns that I'm solving for. And I have 2 different rate expressions, but otherwise it's the same, one and the same.